Your computer flips a coin, heads or tails. You assume it's random, but here's what nobody tells you. It's not. That coin flip was decided the moment your processor started. Every random number your phone generates, every password, every encryption key protecting your bank account, calculated. Predictable. A very smart attacker with the right tools could reverse engineer the entire sequence. This isn't a problem we'll face someday. This is happening now. Hackers exploit predictable random numbers to break into systems every single day. Financial transactions get intercepted. Military communications get decoded. Casino machines get cracked wide open. But there's a solution sitting in the one place nothing in the universe can predict: quantum mechanics. And you're about to see every method we've built to capture that randomness. If you value documented quantum physics and cryptography history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from Nature Communications, published June 2016, and NPJ Quantum Information from the same year, plus recent papers from Physical Review. Applied published October 2024, and Nature Communications from January 2021. These aren't pop science outlets. These are peer-reviewed journals where physicists stake their careers on accuracy. Now back to the information. You need to understand what makes quantum randomness different. Classical physics is deterministic. You throw a die, and if you knew every force, every air current, every microscopic imperfection in that die, you could calculate where it lands. Same with computers. They run algorithms, deterministic mathematical sequences that look random but aren't. They're called pseudo-random number generators. Feed them a seed value, and they'll spit out the same sequence every single time. That's why hackers target the seed. Get the seed, break the system. But quantum mechanics doesn't work that way. When a photon hits a beam splitter, piece of glass that splits light, it either goes through or bounces back. You can't predict which path it takes. Not because you lack information, because the photon itself doesn't decide until the moment it's measured. This is fundamental quantum uncertainty. The universe rolling dice at the atomic level. And this is what we harness. The beam splitter has two outputs. Place a detector at each output. The photon triggers one detector or the other. Assign 0 to one detector, 1 to the other. That's your random bit. Repeat this process and you build a random number stream. The first implementations appeared in the early 2000s. Researchers at Los Alamos and the University of Geneva demonstrated systems generating random bits at kilobit per second rates. Not fast, but provably random. The key limitation was detector dead time, the recovery period after each photon detection. Single photon detectors from that era needed microseconds to reset. This throttled generation rates to maybe 1 megabit per second at best. But the principle was solid. The photon's path choice is pure quantum mechanics, no hidden variables, no way to predict the outcome. By 2014, researchers were using attenuated laser sources instead of true single photon sources. Cheaper, easier to implement. You take a standard laser diode, dial down the intensity until you're emitting a tiny number of photons per pulse, often less than 1 photon on average. When a photon does appear, it hits the beam splitter. Same quantum randomness, lower cost. Commercial systems appeared shortly after. ID Quantique, a Swiss company founded in 2001, brought beam splitter quantum random number generators to market. Their Quantus product line became industry standard. Generation rates climbed as detector technology improved. By 2020, beam splitter systems were hitting 10 to 20 megabits per second with off-the-shelf components. Not the fastest method anymore, but reliable. Simple optical setup, easy to model, straightforward security analysis. Defense contractors loved them. Banking systems deployed them. Any application needing certifiable randomness, but not requiring gigabit speeds. A group at the Technical University of Denmark demonstrated a beam splitter quantum random number generator on a silicon chip in 2019. The entire system, laser, beam splitter, detectors, electronics, fit on a die measuring 3 millimeters by 4 millimeters, power consumption under 1 watt. This was integration that mattered. No longer laboratory equipment, no longer expensive, small enough and cheap enough to embed in consumer devices, SK Telecom noticed. In May 2020, Samsung announced the Galaxy A quantum smartphone, the world's first consumer phone with an embedded quantum random number generator chip. The chip came from ID Quantique, measuring 2.5 millimeters on each side. Smaller than a grain of rice. It generates random numbers used to encrypt authentication data, fingerprints, facial recognition, payment information. The phone shows a quantum indicator on the status bar when apps use quantum security. This wasn't a prototype, this was mass production. As of 2024, Samsung has released 6 generations of quantum phones, Galaxy Quantum 1 through 6. Each model sold in South Korea through SK Telecom. Prices comparable to flagship phones, features matching Samsung's top-tier devices. Quantum security became a selling point, not a novelty. Quantum field theory tells us the vacuum contains zero-point energy, the lowest possible energy state, but not zero. This energy manifests as random fluctuations in electromagnetic fields. Even in a perfect vacuum, with no photons present, the electric and magnetic fields fluctuate. These fluctuations are quantum mechanical noise, fundamentally random and impossible to predict. We can measure this noise. Here's how. You need a laser, a local oscillator, and a beam splitter. Send the laser beam to one input of the beam splitter. Leave the other input empty. That's your vacuum port. The two outputs go to photodetectors in a balanced homodyne detector configuration. The photodetectors measure the light intensity. Because one input has a vacuum state, you're effectively measuring vacuum fluctuations. The detector outputs fluctuate randomly. Sample these fluctuations with an analog to digital converter, and you have raw random data. Their system, publicly accessible online at qrng.anu.edu.au, generates random numbers in real time. Users worldwide can download genuine quantum random numbers derived from vacuum noise. The ANU implementation achieves generation rates around 1 gigabit per second, much faster than beam splitter methods. The reason is detector technology. Homodyne detection uses standard photodiodes, not single photon detectors. Photodiodes have no dead time issue. They respond at gigahertz speeds. Sample the output fast enough and randomness pours out. But there's a catch. The random signal is buried in classical noise, electronic noise from the detectors, laser intensity. Noise, thermal noise. You must characterize every noise source and prove the quantum noise dominates. This requires careful modeling and continuous monitoring. If the vacuum contribution drops below a threshold, the system must shut down immediately. You can't let classical noise masquerade as quantum randomness. Published in Nature Communications, their work developed rigorous bounds on extractable randomness, assuming quantum side information. They achieved 2.9 gigabits per second, certified random output with a field programmable gate array, running Toeplitz hashing, a randomness extraction algorithm that distills pure randomness from noisy data. The FPGA processed raw data in real time, computing hash functions fast enough to keep pace with the detectors. This was critical. Previous systems generated raw bits at gigabit speeds but couldn't extract randomness quickly enough. The ETH Zurich team closed that gap. Their system was practical, deployable, ready for integration into communication networks. Commercial variants followed. ID Quantique's Quantus product line expanded to include vacuum noise generators. Qside Technologies in Barcelona developed the Ruby chip, a vacuum state quantum random number generator qualified for space applications. Radiation hard, compact, low power. The chip flew on satellite missions starting in 2023. Quantum randomness in orbit, used for quantum key distribution experiments and secure satellite communications. The most recent development came in September 2025. Researchers at Chinese Academy of Sciences published work on a chip-scale vacuum state generator achieving 5.2 megabits per second real-time output in a ceramic package. 16.6 millimeters by 7.8 millimeters. The quantum entropy source integrated a Y-splitter waveguide, laser diode, photodetectors, and transimpedance amplifier. The electronics included a microcontroller, analog to digital converter, and randomness extractor. Complete system and package. Low cost, high reliability, mass production ready. This is the trajectory. Laboratory equipment becomes chip-scale products. Gigabit rates become standard. Cost per unit drops below $10. Quantum random number generation transitions from specialized hardware to commodity components. Method number 3, laser phase. Noise. Lasers have phase fluctuations from spontaneous emission in the cavity. Each spontaneous photon adds random phase to the field, creating phase diffusion, a quantum random walk. Convert this to numbers using an unbalanced Mach-Zehnder interferometer. Split the laser, send one beam through a delay line, recombine them. The delayed beam has diffused phase. Interference creates random intensity. Sample with an analog to digital converter. Random phase becomes random bits. Choose parameters correctly, and you get phase variations at gigahertz rates. In 2012, researchers at Tsinghua University demonstrated 6 gigabits per second using a continuous wave laser and homodyne detection. The interferometer required active stabilization, temperature control, and feedback loops to maintain the correct phase relationship. Complicated, but it worked. The breakthrough came with gain-switched lasers. Instead of running the laser continuously, you pulse it. Drive the laser current below threshold between pulses. Each pulse starts from noise and builds up, accumulating large phase diffusion. The phase of each pulse is essentially random. Now you don't need a stable interferometer. The phase diffusion per pulse is large enough that small drifts don't matter. Researchers in Spain demonstrated this in 2015. They achieved 43 gigabits per second using a gain-switched laser and integrated interferometer on an indium phosphide chip. The entire system fit on a photonic integrated circuit. The chip included 2 distributed feedback lasers, multimode interferometer, and photodetectors. Generation rate 43 gigabits per second raw data. After randomness extraction, the output reached multiple gigabits per second of certified random bits. Gigabits per second. Published in Review of Scientific Instruments, they used a laser operating near threshold, highly unstable maximum phase noise. The setup required a very stable interferometer and high-speed sampling. They achieved it with a custom analog to digital converter card sampling at multiple gigasamples per second. The random bits passed NIST statistical tests, the standard battery of randomness tests used to certify cryptographic grade randomness. This was the fastest quantum random number generator demonstrated at the time, but it stayed in the lab. Too complex, too expensive, too sensitive to environmental perturbations. What mattered more was practical deployment. In 2020, researchers published a standardized testing framework for phase noise quantum random number generators. The paper, appearing in July 2025 on arXiv, established quality metrics that system operators could use to continuously monitor their devices. The method checked for independence and uniformity without requiring detailed device models. If the statistical tests passed, the device was operating correctly. If not, shut it down. Simple, robust, practical. This enabled commercial deployment with confidence. Companies could sell phase noise quantum random number generators knowing customers could verify proper operation. Oldest method, dating to the 1950s. Decay is fundamentally random. Quantum mechanics says we cannot predict when individual atoms decay. Constant probability over time, but exact timing unknowable. True randomness. Capture with Geiger counter. Setup is simple. Americium-2, 41 source, half-life 432 years. Geiger-Miller tube detects decay events. Each detection produces a pulse. Time between pulses follows Poisson statistics. Sample a clock when pulse arrives, clock value becomes random number. The server runs continuously, generating random numbers from radioactive decay and making them available online. Users can download random bytes for cryptographic applications, simulations, games, anything needing true randomness. The system compares intervals between consecutive pulses. If the first interval is longer, output 0. If the second is longer, output 1. This removes bias from non-uniform detection efficiency. The generator has run for nearly 30 years without interruption. Proof that radioactive quantum random number generators are reliable, but there are problems. Low bit rate, typically a few bits per second, with a safe, low-activity source. Safety concerns. You're handling radioactive material. Requires proper shielding, licensing, disposal procedures. Not suitable for consumer devices. And the distribution is non-uniform without careful processing. Background radiation adds noise. Detector dead time introduces correlations. These issues are solvable but add complexity. In July 2022, researchers published in Nature Communications a security proof for radioactive quantum random number generators based on parity symmetry. Published by a team at Riken in Japan, the proof doesn't rely on timing measurements, which can be manipulated, but on the direction of particle emission. Radioactive decays emit particles isotropically, with uniform probability in all directions. Measure the direction using a detector array. The direction is random and guaranteed by parity symmetry, a fundamental law of particle physics. This removes trust assumptions about the detector timing circuits. Even if an attacker controls the timing hardware, they can't fake the directional randomness without violating fundamental physics. The proof was device independent in the sense that security relies only on parity symmetry, not on detailed device characterization. This was a significant advance. Radioactive quantum random number generators became provably secure under minimal assumptions. Quantaglion, a commercial company, now sells radioactive quantum random number generator chips using Americium-2 41. The chips are tiny, a few square millimeters, fully shielded with no external radiation, certified safe for consumer use. Generation rates remain low, maybe a few bits per second, but the randomness is unquestionable. Method number 5. Photon arrival time and counting. Instead of path measurement, measure arrival time. Attenuated pulses to detector, small photon number per pulse. When photon arrives, detector clicks. Arrival time relative to pulse is random Poisson statistics. Sample high-speed clock at detection, multiple bits per photon, log base 2 of time resolution, 1 gigahertz clock, 1 microsecond window gives 10 bits per photon. NIST demonstrated this in 2004 at megabit rates with telecom components. Second photon. This caps the detection rate. Worse, dead time introduces correlations between successive measurements. If a photon arrives during dead time, it goes undetected, biasing the statistics. You must account for this in the randomness extraction. Teams at University of Geneva developed models for dead time effects in 2017. Published in scientific reports, they showed how to compute min entropy, the worst-case measure of randomness, in the presence of detector dead time, dark counts, and afterpulsing. They demonstrated a working system generating random numbers with full security analysis. The system used fiber optics, a 640 nanometer laser, and 2 single photon counting modules. Generation rate limited by detector dead time to kilobit per second scale after randomness extraction. Not fast, but certifiably random and provably secure. Instead of measuring arrival time, count how many photons arrive in each time window. Weak light sources emit photons with Poisson distribution, sometimes 0 photons, sometimes 1, occasionally 2 or more. The exact count per window is random. Use a photon number resolving detector, typically a silicon photomultiplier, to count photons. The count value becomes your random number. Researchers demonstrated this in ACS Omega in September 2023. They used a silicon photomultiplier to resolve photon numbers in attenuated light. The detector response signals integrated over time to resolve photon counts. The system generated 4-bit sequences at 13.6 megabits per second. Low cost, simple components, easily miniaturized. The random bits passed NIST statistical tests. This approach is attractive for embedded systems. Silicon photomultipliers are solid-state devices, rugged and compact. No moving parts, no fragile optics. Suitable for IoT devices, edge computing, harsh environments. Generation rates are modest but sufficient for many applications. All previous methods assume you trust your hardware. You trust the detectors measure what they claim. You trust the source emits the quantum states you expect. But what if the devices are compromised? What if an attacker has tampered with your equipment? Device-independent quantum random number generation solves this. The security relies solely on observed correlations, not on trust in the hardware. The method uses entangled photon pairs. Generate pairs using spontaneous parametric down conversion. Send 1 photon to Alice, 1 to Bob. Alice and Bob are spatially separated, far enough that no signal can travel between them during a measurement. Alice and Bob each choose a measurement setting randomly and measure their photon. They record the outcomes. If the photons are entangled, the outcomes will be correlated in a way that violates a Bell inequality, a mathematical bound that classical physics cannot exceed. Quantum mechanics violates Bell inequalities. The amount of violation certifies how much randomness the measurements contain. This is the key insight. Bell inequality violation proves the outcomes cannot be predetermined. An attacker cannot have programmed the results in advance because no local hidden variable theory can produce Bell violation. Roger Kent. They showed that measuring entangled particles and checking for Bell violation allows randomness certification without trusting the devices. The catch is detection efficiency. You need high-efficiency detectors, above 66%, where the loopholes remain open. Single photon detectors in the early 2000s had efficiencies around 20 to 30%, not good enough. For years, device-independent quantum random number generation remained theoretical. The breakthrough came in 2015. A team at NIST demonstrated a loophole-free Bell test using entangled photons and high-efficiency superconducting detectors. Detection efficiency exceeded 90%. Spatial separation eliminated signaling loopholes. The test closed all known loopholes and confirmed Bell violation with overwhelming statistical significance. This opened the door for device-independent quantum random number generation. In 2018, researchers in China demonstrated device-independent randomness generation using entangled photons. They violated the Clauser-Horn-Chamonix-Holt inequality, a standard Bell inequality, and extracted certified random bits. The generation rate was low, bits per hour, not bits per second. The reason is statistics. Certifying randomness requires collecting enough data to rule out statistical flukes. With photon loss and finite detection efficiency, this takes time. Recent advances improved device-independent quantum random number generation rates significantly. In October 2024, researchers optimized the choice of Bell inequality and measurement settings to maximize certified randomness. Published in Physical Review Applied, the work showed that certain Bell inequalities perform better than others depending on the noise level. By selecting the optimal inequality for the experimental conditions, they increased the certified randomness by factors of 2 to 5 compared to standard approaches. This moved device-independent quantum random number generation closer to practical speeds. but it remains the slowest and most complex method. The requirement for high-efficiency detectors, spatial separation, and extensive statistical analysis makes deployment difficult. Commercial device-independent quantum random number generators don't exist as of 2025. They remain research tools, used primarily for fundamental tests of quantum mechanics and ultimate security applications where no other method suffices. You make minimal assumptions about the devices, for example, that they operate in a bounded Hilbert space dimension. But you don't trust everything. These schemes use weaker tests than Bell inequalities, but still provide security guarantees. Measurement device independent quantum random number generation is one variant. You trust the source, but not the detectors. This is realistic because sources are easier to characterize and control than detectors. Detectors have side channels, timing information, photon number resolution, efficiency variations. An attacker could exploit these without touching the source. Measurement device independent schemes place the untrusted detectors at a remote location controlled by a third party. Alice sends quantum states to the measurement device. The device performs a measurement and announces the outcome. Alice doesn't need to trust the device because her security relies on the source preparation, not on what the device actually did. Researchers at University of Toronto demonstrated measurement device independent quantum random number generation in 2015. Published in New Journal of Physics, the work showed loss-tolerant generation without requiring high detector efficiency. The system used coherent states and photon interference to generate randomness. Because coherent states are robust against loss, the scheme worked even with realistic detector efficiencies below 50%. This made it practical. You could deploy measurement device independent quantum random number generators over telecom fiber with off-the-shelf components. Useful when you can't characterize the source accurately. Maybe it's provided by an untrusted vendor, or operates in a regime where modeling is difficult. The scheme measures two quadratures of the light field simultaneously and uses the correlation between measurements to bound the entropy. This doesn't require assumptions about the source state, only that the measurements are well characterized. Teams at University of York demonstrated source-independent quantum random number generation in 2021. The system measured orthogonal quadratures using balanced homodyne detection. Generation rates reached gigabit per second scale with standard optical components. Security analysis accounted for quantum side information and finite size effects. The output passed standard randomness tests and met cryptographic requirements. Source-independent quantum random number generation is attractive for commercial deployment because it removes the burden of precisely characterizing laser sources. Lasers vary with temperature, aging, manufacturing tolerances. With source independence, these variations don't matter. Security is guaranteed as long as the detectors work correctly. Quantum key distribution systems need random numbers to choose measurement bases. If the random numbers are predictable, the entire protocol fails. Quantum random number generators provide certified randomness for this purpose. ID Quantique's quantum key distribution systems integrate Quantis quantum random number generators directly. The random numbers never leave the secure hardware. They're generated, used immediately, then discarded. No external interface, no opportunity for extraction or prediction. Financial sector, next. High-frequency trading algorithms use random numbers for strategy selection and order timing. Predictable randomness gives competitors an edge. Banks now deploy quantum random number generators in trading systems. A single trade worth millions of dollars cannot afford compromised randomness. Several major financial institutions have installed quantum random number generator racks in their data centers. Not disclosed publicly, security through obscurity is still valued, but the deployments are real. Encryption keys for classified communications must be unbreakable. Predictable random numbers compromise national security. The U.S. National Security Agency certifies quantum random number generators for use in classified systems. The certification process is brutal. Months of testing, statistical analysis, side channel evaluation. Devices that pass become approved for top secret applications. Many governments now require quantum random number generation for high security systems. Not recommended, required by policy. Satellite communications adopted quantum random number generators starting in 2020. The Ruby chip from QSide Technologies flew on European Space Agency missions. Radiation-hardened, space-qualified, generating megabits per second in orbit, used for quantum key distribution experiments between satellites and ground stations. The randomness survives the space environment, cosmic rays, temperature extremes, vacuum. This proves quantum random number generators are deployable in extreme conditions, not just comfortable laboratories. 6 generations of Samsung Galaxy quantum phones now in circulation. Each with ID Quantique's 2.5mm quantum random number generator chip, used for authentication, payment encryption, secure storage. The phones aren't expensive, price comparable to flagship models without quantum security. SK Telecom sells them in South Korea. Other regions have different quantum phone models. V-Smart Air is 5G in Vietnam. Both use ID Quantique chips. As of December 2024, the Galaxy Quantum 5 launched with enhanced AI features and premium hardware. The quantum random number generator remains, now integrated with more apps and services. Banking apps use it for transaction signing. Social media apps use it for secure messaging. Games use it for anti-cheat systems. The quantum indicator on the status bar tells users when quantum security is active. Users can see in real time when their data is protected by quantum physics. IoT devices are next. Billions of connected sensors need security. Quantum random number generators offer compact, low-power, provably secure solutions. Manufacturers integrate chips into high-value targets: industrial controllers, medical devices, automotive systems. $5 to $10 per chip currently. Within 5 years, expect sub-$1 chips, making them viable for commodity devices. Randomness as a service emerged. ANU's server provides free bits since 2016. Now AWS and Azure develop commercial services. Users connect via API, request bits, pay per use. Cloud-based randomness could become a multi-million-dollar market within a decade. All components, laser, waveguides, detectors, processing, on a single silicon die. No external optics, no fiber coupling, no alignment. Plug it in, turn it on, get randomness. Several groups are close. Researchers at MIT demonstrated a fully integrated quantum random number generator in 2023 using silicon photonics. Chip size 5 millimeters by 5 millimeters. Generation rate 100 megabits per second. Power consumption under half a watt. CMOS compatible fabrication, meaning it can be manufactured in existing semiconductor fabs. No special processes, no exotic materials. Once silicon photonics quantum random number generators reach mass production, costs will plummet. A chip costing cents, not dollars. At that point, every device gets quantum randomness. Smartphones, laptops, routers, servers, IoT gadgets, even smart cards. Quantum random number generators become as ubiquitous as transistors. How do you know your quantum random number generator is working correctly? Continuous self-testing is the answer. The device runs internal checks, comparing observed statistics against theoretical predictions. If the statistics drift outside acceptable bounds, the device shuts down and alerts the operator. This is already implemented in commercial systems. ID Quantique's Quantis chips include health monitoring. The chip measures shot noise levels, detector balance, and output statistics. If anything looks wrong, the random stream stops immediately. No bad randomness ever reaches the application. This level of vigilance is necessary. A malfunctioning quantum random number generator is worse than no quantum random number generator at all, because the user thinks they have security but actually don't. Detection of failure is as important as generation of randomness. Standards will emerge. Currently, no international standard defines what makes a quantum random number generator acceptable for security applications. NIST has guidance for classical random number generators in Special Publication 822 and Special Publication 890. These documents cover testing methods and entropy estimation. Quantum random number generators need similar standards. The International Organization for Standardization is working on this. ISO working groups are drafting standards for quantum random number generation, covering everything from device characterization to statistical testing to security evaluation. Expect published standards by 2027. Once standards exist, certification programs will follow. Labs will offer quantum random number generator certification services. Manufacturers will submit devices for testing. Certified devices get a seal of approval. Government and enterprise buyers will require certification. This creates a compliance market, ensuring only well-designed quantum random number generators get deployed in security-critical systems. The strangest application is fundamental physics tests. Quantum random number generators can close the freedom of choice loophole in Bell tests. This loophole says that maybe the measurement settings aren't truly random. Maybe they're correlated with the hidden variables determining the measurement outcomes. If so, Bell inequality violation doesn't prove non-locality. To close the loophole, the measurement settings must be chosen by random numbers generated faster than light can travel between. The particles. Quantum random number generators provide those random numbers. In 2017, the big Bell test collaboration used human choices and quantum random number generators to select measurement settings in Bell tests performed around the world simultaneously. Over 100,000 people participated, generating random bits by playing online games. Those bits combined with quantum random number generator output, determined the measurement settings. The tests confirmed Bell violation, closing the freedom of choice loophole with human and quantum randomness. This wasn't just a physics experiment, it was a demonstration that quantum randomness is trustworthy enough for the most demanding tests of reality itself. This classical noise is not fundamentally random, it's just complicated. An attacker with detailed knowledge of the hardware could, in principle, predict it. So you must quantify how much quantum randomness you have versus how much classical noise you have. This is entropy estimation. You model every noise source, you measure the system parameters. You compute the mine entropy, the worst case randomness assuming the attacker knows everything except the quantum contribution. Then you apply a randomness extractor, a cryptographic hash function that takes the noisy raw data and outputs pure randomness. The extractor compresses the data, outputting fewer bits than you put in, but those output bits are uniformly random, even if the input was biased or correlated. This is critical. Without extraction, raw quantum random number generator output is not usable for cryptography. It's biased, it's correlated, it's mixed with classical noise. Extraction fixes this. The trade-off is speed. A quantum random number generator might produce 10 gigabits per second raw data, but only 5 gigabits per second after extraction. You multiply your raw data by a large Toeplitz matrix, a matrix with constant diagonals, then take the result modulo 2. The matrix is filled with random bits, chosen once during setup. The output is uniformly random if the input has sufficient min entropy. Researchers at ETHZ developed efficient Toeplitz hashing implementations running on FPGAs. Published in Nature Communications in 2021, their work achieved multi-gigabit per second extraction rates. The FPGA applies the hash in real time, keeping pace with the quantum random number generator. No buffering, no latency. Random bits flow continuously from generation to extraction to output. This is what makes modern quantum random number generators practical. Fast extraction enables fast generation. In 2025, approximately 8 commercial companies sell quantum random number generator products. ID Quantique leads the market with multiple product lines: Quantus PCIe cards, USB devices, rack mount systems, and the mobile chip. QSide Technologies offers the Ruby chip and rack mount systems. Quantum Numbers Corporation in Australia commercializes ANU's vacuum noise technology. Olea Quantum Technologies in Denmark sells photonic quantum random number generators. BTRE in South Korea manufactures quantum random number generator chips for mobile devices. Quantaglion in Japan sells radioactive decay quantum random number generators. New Quantum in the UK develops integrated photonic quantum random number generators. QNU Labs in India offers Tropos, a quantum random number generator based on photon arrival time. This is a real market, not a lab curiosity. Annual revenue is likely in tens of millions of dollars, approaching 100 million within 5 years as mobile and IoT adoption accelerates. The sixth model, Galaxy Quantum 6, launched in 2025. Same 2.5mm chip, same quantum security, expanded application support, banking apps, government services, secure messaging, encrypted storage. The quantum indicator shows users when quantum security protects their data. This is transparency. Users see the technology working. They understand, at some level, that quantum physics is securing their information. This builds trust. Trust drives adoption. Adoption drives volume. Volume drives cost reduction, a virtuous cycle. Within a decade, quantum random number generators in consumer devices could be as common as fingerprint sensors or cameras. New methods appear regularly. In 2024, researchers demonstrated quantum random number generation using quantum dots, nanoscale semiconductor structures that emit single photons. The dots are embedded in chips, electrically driven, room temperature operation. Generation rates reach megabits per second with compact form factor. Another approach uses nitrogen vacancy centers in diamond. These are atomic scale defects in diamond crystal that emit single photons when illuminated. The emission timing is quantum random. Researchers demonstrated quantum random number generators with diamond chips smaller than 1 millimeter on a side. Solid state, no moving parts, extremely rugged. Suitable for military applications, space missions, anywhere reliability matters more than cost. These methods aren't mainstream yet, but they show the field is still innovating. Quantum random number generation isn't solved, it's evolving. New protocols using multipartite entanglement promise faster rates. Instead of 2 entangled particles, use 3 or 4 or more. The correlations become richer, more randomness per measurement. Researchers demonstrated this concept in 2024 using photonic chips with 3 photon states. The generation rate tripled compared to 2 photon schemes. Scaling to larger systems could increase rates further, but engineering challenges multiply. Generating and detecting many particle-entangled states is hard, currently achievable only in research labs. But if solved, multipartite device-independent quantum random number generators could reach gigabit speeds with ultimate security. Quantum key distribution needs randomness, but quantum random number generators can provide more. Randomness expansion takes a small amount of initial randomness and amplifies it to large amounts using quantum measurements. This was proposed theoretically in 2012 and demonstrated experimentally in 2018. The protocol uses entangled photons and Bell tests to certify that the expanded randomness genuinely came from quantum mechanics, not from the initial seed. This means you can start with a weak, possibly compromised random seed and produce strong, certifiable randomness. Applications include scenarios where you inherit random numbers from an untrusted source, maybe a legacy system or a third-party vendor, and need to amplify them to secure levels. Randomness expansion does this without requiring trust in the input. Data centers generate quantum randomness and distribute it worldwide. Users request bits on demand. The randomness is certified, authenticated, and encrypted in transit. No user device needs local quantum random number generation hardware. Everything connects to the network. This model centralizes quantum hardware in professionally managed facilities, ensuring high reliability and continuous monitoring. It decentralizes access, making quantum randomness available to any device anywhere. Building this network requires infrastructure, quantum random number generator farms, high-speed data links, authentication protocols. But it's technically feasible with existing technology. Some pieces already exist. Cloud providers offer randomness APIs. Quantum hardware manufacturers sell rack-mount systems. The missing component is standardization and trust. Users must believe the network delivers genuine quantum randomness and that it isn't logged, tampered with, or compromised. This requires third-party audits, transparency, and regulatory oversight. Achieving that takes time. Here's the reality check. Despite decades of development and millions of dollars invested, quantum random number generators remain niche products. Most organizations use classical random number generators because they're cheaper, simpler, and good. Enough for most purposes. Quantum random number generators shine in extreme security applications. Government, military, finance, critical infrastructure. For everyone else, the cost-benefit ratio isn't compelling yet. But that's changing. As quantum computers become more powerful, classical cryptography becomes vulnerable. Algorithms like RSA and elliptic curve encryption rely on computational hardness. Factoring large numbers or solving discrete logarithms is difficult for classical computers. Quantum computers will break these algorithms. Shor's algorithm, published in 1994, shows how a quantum computer can factor large numbers efficiently. Once quantum computers are large enough, maybe 1 million qubits, they'll crack RSA keys in hours. This threat drives adoption of post-quantum cryptography, new algorithms resistant to quantum attacks. But post-quantum algorithms still need random numbers, strong random numbers. Quantum random number generators provide that. They're quantum safe by definition. A quantum attacker cannot predict quantum randomness because predicting quantum measurement outcomes violates the foundations of quantum mechanics. NIST selected post-quantum algorithms in 2022. Standardization continues through 2025. Deployment will extend into the 2030s. Throughout this transition, organizations need trust in their random number generation. Quantum random number generators offer that trust. They're not vulnerable to algorithmic advances or increased computing power because they don't rely on computational hardness. They rely on physics, and physics doesn't change with Moore's law. This makes quantum random number generators future-proof. Buy a quantum random number generator today, and it's secure against quantum computers 20 years from now. Classical random number generators can't make that claim. The thing that makes all this work is verification. You can't see randomness. You can't inspect a number and say whether it's truly random. Randomness is a property of the process, not the outcome. So you test the process. You run statistical tests, NIST 822, diehard, test U01, ENT. You measure entropy rates, autocorrelation, frequency distributions, run lengths. If the output passes all tests, you accept it as random. If it fails, you investigate. Maybe the hardware malfunctioned. Maybe someone tampered with it. Maybe your model was wrong. Commercial quantum random number generators include continuous testing. The device tests itself automatically all the time. If a test fails, the output stops immediately. This self-checking is what makes quantum random number generators trustworthy. You don't have to believe the vendor's claims. The device proves its operation every second. Quantum random number generation is the simplest quantum technology. simpler than quantum key distribution, quantum computing, quantum sensing. It requires only one quantum effect, measurement randomness, and minimal quantum control. No need for long coherence times, error correction, or entanglement distribution. Just shine light, detect it, measure the noise. This simplicity explains why quantum random number generators commercialized first. They reached the market in 2001. ID Quantique's Quantis launched that year. Quantum computers are still prototype scale. Quantum communication networks are experimental. But quantum random number generators are products, available off the shelf, deployed in production systems, generating certified random bits 24 hours a day, 7 days a week, for years without failure. This is quantum technology that works now. In 2023, ID Quantique published data showing their mobile quantum random number generator chips have shipped in quantities exceeding 1 million units. 1 million quantum devices in consumers' pockets. Generating quantum randomness every time someone unlocks their phone, makes a payment, stores data. This isn't coming. This is here. Quantum physics protecting everyday life. Not in a lab. In Seoul, Hanoi, wherever these phones are sold. The quantum revolution started quietly with random numbers, not with quantum computers solving unsolvable problems, not with quantum teleportation sending information faster than light, with photons hitting beam splitters and triggering detectors, with vacuum noise generating random voltages, with radioactive atoms decaying unpredictably. These simple quantum effects turned into chips, deployed at scale, securing the digital world. And most people have no idea it's happening.